data for automated training of machine learning models that classify text into categories. And dataset structures, it is of a labeled dataset with two main columns. Text includes example sentences, documents, etc., and corresponding label category or class. And data usually formatted as CSV or JSON or specialized ML table formats, depending on platforms. And key steps in loading text data in AutoML. Those are data collection and cleaning, upload data, specify target columns, or train validation split, sampling large data sets, and handling imbalanced classes. So these are the six things which comes under key steps in loading text data into AutoML. So first we will see data collection and cleaning. Gather text samples with accurate category labels, pre-processed text for consistency. Optional as some AutoML tools handle raw text, and upload data set to cloud storage linked with AutoML platforms, and ensure text and label fields are clearly specified. And next is a specify target column. During setup, define the label column as the target for classification. Train validation split. AutoML framework often allow manual or automatic splitting. Common splits include 80% training and 20% validation, and some platforms support providing separate validation datasets. And sampling large datasets, for very large datasets, AutoML applies stratified sampling to preserve class distributions. And sampling helps manage memory and training time without losing representativeness. And handling imbalance classes, for this, AutoML may use techniques like downsampling majority classes and applying class weights to balance the training. And balancing is applied only to training data to keep evaluation fair. And supported platform examples like Azure AutoML supports specifying language, hyperparameters, job limits, and datasets in ML table format. And Amazon SageMaker Autopilot allows API-based dataset upload with options to control splits and validation fraction. And AutoKeras, example of manual train or validation or test split with Python code for dataset loading and training. And best practices include like ensure the data is well labeled and representative, and use stratified splits to maintain class balance, and provide separate validation data if possible for unbiased training or tuning, and monitor class imbalance and use weights or sampling if necessary. And summary is loading a text classification datasets into AutoML involves careful preparation of labeled text data, and also specifying the target label, and managing training and validation splits, and handling large data scales through sampling and balancing strategies. These steps enable scalable, efficient, automated model training, essential knowledge for AI and data science students. So these are the references for the particular nodes. And we are moving to the handling large data sets in AutoML. So what are those? So handling large data sets in AutoML brings challenges related to computational resources, data preprocessing, and model interpretability. And AutoML automates many tasks like feature engineering, model selection, hyperparameter tuning. But scaling these for massive data needs optimizations. So computational challenges. What are the challenges you have in handling large data sets? Like training on millions of rows is time consuming and resource intensive. And trial and error search for best models, hyperparameters multiplies compute time, and tasks like cross validation multiply data processing workflow, and straining memory and storage. Efficient pipeline design example, sparse formats sampling is often required. And data pre-processing concerns like large data sets often noisy with missing values, irrelevant or redundant features, or terminal struggles with very high cardinality or categorical variables or very large feature sets without manual prep. Also, like pre-processing techniques such as aggregation, embeddings, samplings, and feature selections can help, but add complexity to that data pre-processing process. And model interpretability and maintenance, like large data sets usually result in complex models, ensembles, and deep nets, which is harder to explain and maintain. And retraining a data evolves can be costly and slow, complicating real-time applications. Balancing model performance with transparency and maintainability is very critical. And moving on to the scaling strategies, like use distributed computing and specialized hardware GPUs clusters for training. Employ big data frameworks to enable scalable pre-processing and model training, and data partitioning and incremental learning help manage resource constraints. Sampling and dimensionality reduction reduce data size without losing key information. And here best practices are plan resource allocation carefully based on dataset size and complexity. That is very important. And combine automation with manual intervention for pre-processing, and monitor model complexity and implement custom monitoring for deployed models. And conclusion is like AutoML for large scale data requires balancing automation benefits with practical constraints and system design improvements. Understanding understanding these trade-offs is essential for effective use of AutoML in real-world big data projects. And that's all about the handling large data sets in general. And now we will move on to the next topic, which is parallelization on multiple GPUs in scaling up AutoML. So, what is parallelization on multiple GPUs? Parallelization on multiple GPUs accelerates AutoML workflows by distributing compute-intensive tasks such as model training and hyperparameter search. So these two are the main things when you distribute compute intensive tasks to accelerate AutoML workflows. Where parallelization on multiple GPUs accelerates on AutoML workflows, mainly concerned with this computing intensive tasks like what model training and hyperparameter research, because it occupies or takes away major compute processes or resources. So that is why they mentioned as compute intensive tasks. And why parallelize in AutoML? So AutoML often involves numerous trials exploring different models and hyperparameters. GPU parallelism enables simultaneous evaluation of multiple trials or speeds up large model trainings. And parallelization strategies like data parallelization, model parallelization, and task parallelism. And we will see one by one. What is data parallelism? So it is replicates the model across GPUs. Each GPU process a subset of the data batch. Gradients are aggregated and synchronized to update model parameters suitable for large datasets with fixed model architecture. And model parallelism like splits the model itself across GPUs, useful for very large models that cannot fit into a single GPU's memory. Task parallelism runs multiple AutoML trials concurrently on different GPUs, and each GPU works independently on different hyperparameters or architecture configuration. And next is implementation in AutoML frameworks. Like how do you implement this parallelism uh, of multiple GPUs? So Using the above three strategies, like we have to implement the parallelism of GPUs in the AutoML, like AutoML frameworks, uh, which can be achieved by support for distributed training and parallel search is integrated in platforms like Google Cloud AutoML, Microsoft Azure AutoML, and open source libraries. Tools like Horoword and PyTorch distributed facilitate multi GPU parallelism. And the benefits of multi parallelism in multiple GPUs are like benefits which are significant reduction in time for model training and hyperparameter optimization and ability to scale AutoML to bigger data sets and more complex model searches. The challenges are requires careful synchronization of model updates, especially in data parallelism, and communication overhead across GPUs can limit scalability. Efficient utilization demands compatible hardware and optimized code. And best practices are use mixed precision and batch size tuning to maximize GPU utilization, balance workload to avoid ideal GPUs, monitor training to detect bottlenecks or communication delays. So that's all about the parallelism of or parallelization of multiple GPUs in autonomous frameworks. And just hold on a second. Going back, let us start with the data parallelism. So, what is data parallelism in scaling up AutoML? Uh, Data parallelism is a distributed computing techniques where the input data set is split across multiple processors, example GPUs, and each process a portion of the data simultaneously while running the same models. And how this data parallelism works. So, the complete model is replicated on each GPU. Each GPU receives a mini batch of training data. GPUs compute gradients independently based on their batch, and gradients from all GPUs are aggregated, synchronized, and used to update model parameters. And this synchronized update ensures all model copies remain identical. That is very important. And advantages in AutoML scaling is like enables efficient processing of large data sets by dividing data across multiple GPUs and speeds up model training without changing model architecture. Straightforward to implement compared to model parallelism. And typical workflow is split data batch into smaller mini batches for each GPUs and parallel forward and backward passes on each GPUs. Use collective communication techniques, example, all reduced to synchronize gradients and update all models simultaneously with synchronized gradients. Challenges like communication overhead during gradient synchronization can limit scalability for very large GPU clusters and requires well optimized communication libraries and hardware support. Batch size per GPU needs to be chosen carefully to balance memory constraints and computational efficiency. And implementation tools like frameworks like TensorFlow, PyTorch provide built-in utilities for data parallel training, and Horoword is a popular open source library that streamlines multiple GPU data parallelism. And best practices like use mixed precision training to reduce memory bandwidth, optimize batch size and learning rate, scaling according to the number of GPUs, monitor GPU utilization and communication delays for performance bottlenecks. Like these are the data parallelism is a key technique to scale AutoML training across multiple GPUs, increasing throughput and reducing time for large-scale machine learning tasks while maintaining model consistencies. And understanding data parallelism is very essential for mastering the scalable A or AutoML system. And next is model parallelism in scaling up AutoML. And this is like Model parallelism is parallel computing techniques where a large machine learning model is divided into smaller parts and each part is processed on different GPUs or device simultaneously. Unlike data parallelism, which replicates the whole model on each device and splits data, model parallelism splits the model itself. So why model parallelism? Why do we want to have a model parallelism? Like essential for model parallelism is essential for training very large models that cannot fit into the memory of a single GPU or device. That is one thing, and which helps to scale model training beyond hardware memory limits. So model parallelism is very useful for this particular reason and common in deep learning models with huge parameters counts, example large transformer models, and types of model parallelism. One is pipeline parallelism, tensor parallelism, and hybrid parallelism. What is pipeline parallelism? Splits more model layers into sequential stages, each running on a different device, and micro batches of data move sequentially through the pipeline stages, allowing concurrent execution. And tensor parallelism splits individual tensor operations horizontally across GPUs. Each GPU handles a shared of tensor for parallel computation and results are combined. And hybrid parallelism like combines data parallelism and model parallelism to optimize resource use and training speeds and working during forward and backward passes data flows between devices corresponding to their assigned model segments. Synchronization is required to pass intermediate results and gradients between GPUs. Communication overhead between devices is a main bottlenecks, and implementation tools like frameworks such as DeepSpeed, Megatron LM, Colossal AI facilitates model parallel training and require advanced management of memory, communication, and synchronization. And this is one important thing while implementation of the model parallelism. And challenges in the model parallelism like increased complexity in programming and debugging, communication overhead between devices can reduce efficiency, needs high bandwidth interconnects, example NVLink to reduce transfer latency, and advantages are like enables training of models much larger than single device memory, supports training of state-of-the-art resource-intensive models in AutoML, best practices like optimized model partitioning to balance workload and minimize data transfer, use pipeline parallelism with micro batching to improve utilization, combined with data parallelism for maximizing throughput, hybrid parallelism. So these are the best practices and summary of the model parallelism or like practitioners a model across multiple devices to overcome hardware memory limits and scale AutoML training for very large models. And it requires careful design to manage inter-device communication and synchronization, making it powerful approach in advanced AI systems. And next is parallel tuning in scaling up AutoML. So, what is parallel tuning? Parallel tuning refers to the process of simultaneous evaluating multiple hyperparameters or model configuration trials across different compute resources and speeding up the hyperparameter optimization phase in AutoML. And what are the importance of parallel tuning is hyperparameter tuning is computationally expensive and time consuming. There is one thing. And parallel tuning leverages distributed computing, multi-core CPUs, multi GPUs or clusters to shorten this time dramatically. And how parallel tuning works. The automobile system generates a set of candidate hyperparameter configuration. These configurations are assigned to different compute nodes or GPUs to be trained and evaluated simultaneously. Results are collected and subsequently, and a candidate's generation may use information from completed trials. Types of parallel tuning techniques like synchronization parallel tuning, asynchronous parallel tuning, and population based evolutionary algorithm, Bayesian optimization with parallel query. So we'll start with synchronous parallel tuning. So in this synchronous parallel tuning type, like waits for all parallel trials in a batch to finish before generating the next set. and simple but can lead to ideal compute resources if some trials finish earlier. And also, like asynchronous parallel tuning is launches new trials as soon as resources becomes free without waiting for all current trials, and more efficient utilization for resources, faster exploration of hyperparameter spaces. That is one advantages in asynchronous parallel tuning. And population based and evolutionary algorithm use population of candidate solutions evolving over time, can be naturally parallelized by evaluating multiple candidates concurrently. And Bayesian optimization with parallel querying extends Bayesian optimization techniques to propose multiple promising configuration in parallel. So these are all the types of parallel tuning techniques, and the challenges in implementing parallel tuning techniques are like managing dependencies or sequential constraints between trials, if any, and efficient scheduling and load balancing to avoid resource wastage, and combining partial results from asynchronous trials for correct tuning decisions, and implementation in automobile platforms or by the following, like most modern AutoML libraries or platforms: Google Vertex AI, Azure AutoML, Learn, support some form of parallel hyperparameter tuning. And frameworks like Raytune and Optuna provides advanced parallel tuning engines supporting distributed systems. And best practices in implementing or like monitor resource utilization and continuously to improve scheduling. Choose asynchronous strategies for large cluster for better efficiency. Balance the balance the number of parallel trials to available compute and task complexity. So, to summarize the parallel tuning, like parallel tuning leverages concurrent trial evaluation to accelerate AutoML's hyperparameter search, and crucial for scaling up AI model development efficiently. Understanding parallel tuning techniques helps A and DS students effectively to design and deploy automable solutions. This help you to design and deploy automable solutions. And next is so this is an additional one to understand designing the acquisition function in AutoML. So acquisition function guides the search of the optimal hyperparameters and models in AutoML by selecting the next data points to evaluate, balances exploration, searching uncertain areas, and exploitation, focusing on known good areas. Working principles like uses a surrogate probabilistic model, example Gaussian process to model objective function behavior. Acquisition function acquisition function scores candidates points using the predicted mean and uncertainty. The point with the highest acquisition value is selected next to the optimized. Common types are like expected improvement EI, probability of improvement PI, upper confidence bound UCB, and entropy search. What is EI? Expected improvement measures expected gain over current best balances between improving, exploring, and probability of improvement PI. The like probability a candidate improves current best can be exploitative. Upper confidence bound ECB combines mean and uncertainty with tunable trade-off parameters. Entropy search focuses on reducing uncertainty about the location of the optimum. Optimization, like acquisition function, is usually optimized by gradient-based methods or evolutionary algorithms often require multiple random restarts to escape local optima. Initialization, good initial samples improve acquisition function performance. Initial samples often generate using Latin hypercube sampling or Sobol sequence. Trade-offs or complex acquisition functions provide better guidance but can be computationally expensive. Single functions like EA provides practical balance, and this covers the concept of practical design of aspects of acquisition functions in AutoML. And that's all from the module 5. Thank you for joining today.